Hello, this is Aaron Sparrowhawk, and I'll be doing a screencast here for 2.3 fatigue and recovery. This one will be particularly on fatigue. So firstly, an intro to fatigue. Fatigue is something that many performers have during or after an activity. One of the most common reasons as to why fatigue happens is harmful waste products such as lactic acid. And that's created over consistent muscular contractions. So for a long-distance runner, for example, they would have a high amount of lactic acid due to the duration of the activity and how long it takes them to finish the marathon. Even though it isn't such a demanding exercise, due to the duration, it's created a large amount of lactic acid in the movement that it requires over the duration. There are many ways in which we can delay fatigue in order to last longer during these events. So some performers will try to avoid fatigue because fatigue has a massive effect on marathon runners. For example, it slows them down, it tires them, and it actually causes pain and triggers pain receptors. One of the ways they prolong is to carbo load before a race. Carbohydrates give them slow release energy, and it also increases carbohydrate stores. Obviously, that's when you run out of carbohydrate stores, that's when you hit the wall as such. However, at times when we're low on fuel and our carbohydrate stores are running out or are too low to use, our body actually goes to our own muscle protein and actually uses our own muscle as fuel for muscular contraction. This isn't a good thing. This isn't a good thing for performers as it affects the muscles, increases pain receptors, and for certain performers, if this actually happens, it will actually have an effect on their bodies for the next few days, so to avoid this will be preferable. After a race or activity, a long period of time of no exercise is required during marathons, so their body actually has time to recover from all the carbohydrate stores that's been used and any protein that's been used up from their own muscles as energy. So firstly, creatine. Creatine has limited stores in the body and only lasts for 8 to 10 seconds when we're using the creatine. Creatine's ideal would be for really short, intense exercises. So really, a quick sprint towards the football or a 100-meter sprint. Something that's really intense and really quick for a really short duration. However, after using creatine stores, muscles begin to fatigue at a really high rate. So it wouldn't be helpful for athletes with longer duration sports that play for a long time, such as a tennis game can last for hours, or marathons, for example. Using creatine wouldn't actually help them at all. Creatine supplements are taken by many performers. That's to really ensure that you have enough creatine so you can use creatine for a longer duration, so you can stay in that energy source for as long as possible before you have to go to another energy source. We've got some data here. We took it down at Eastbourne, 2 performers, and you can see really that the data show that the person with the lower peak output might have fast glycolytic fibers, which means he'll fatigue quicker in comparison to the second athlete who had a much higher peak power output, but lower fatigue index, which could be due to the person having the right fibers, which is slow oxidative fibers. This shows that the person with a better peak power has more stores of creatine, meaning he will last longer before fatigue. Creatine is vital, and some performers take legal supplements, as we've said before, to ensure that the creatine stores are high and that they can work at a high intensity for a longer period of time, more so than any other performer. Just to point out, most creatine supplements are actually legal. There are some which have been banned by Olympic associations and stuff like that, but most creatine supplements you can buy, and they're not illegal. So next, glucose and glycogen. Glycogen is needed for both anaerobic and aerobic exercises. It's a really common fuel that the body goes to after after, creatine and things like that. It then goes to the glycogen stores, and the body sometimes spares glycogen so it can use it later in the activity, and they actually use this as fuel to resynthesize ATP. And then glucose, on the other hand. Glucose is related to the sugar levels in the blood. They should be consistent and constant. If sugar levels rise, then that will cause a spike of quick energy. However, there will be a plummet, and that will cause what is known as a sugar crash. The way you spike is by taking food or drinks, such as energy drinks or chocolate bars. That's a really quick release energy. But eventually, as I said before, you do have the crash. During exercise, the body will attempt to keep the glucose levels as constant as possible, we said before, but this really is because the brain needs a healthy supply of amount of blood glucose. Blood glucose will drop when glycogen levels become depleted, and glycogen stores are used during medium to long duration activities, such as we said before, the marathon, for example, or a tennis game. As there is lower blood glucose availability, there will be a reduced rate of carbohydrate oxidation, and this will cause slowly, but it will cause fatigue. Hypoglycemia will occur when the blood sugars are extremely low, and as a result it will be a loss of energy, and fatigue in the muscles will set in. Also, to go back to the fatigue amount, it does also create mental fatigue, which then leads to what runners associate with hitting the wall. If blood glucose levels are extremely low, then the brain can't process things, and that's when you start to fatigue and hit the wall mentally. So now waste products. Firstly, CO2. CO2 is found and produced as a waste product in the muscles. The more the muscles are contracting and working, the more CO2 will be present at the muscles. As exercise is taking place and breathing rate increases a high amount, carbon dioxide is increased as a waste product in the muscles, as we said before. The harder the muscles work and contract, the more CO2 is created. So if you're contracting at a really fast, intense rate, the more CO2 will be created as such. Receptors, such as the chemoreceptors, detect the pH level, which is the acidity in the blood, which is affected by CO2. Obviously, the more CO2 you have, the lower the pH goes, due to the acidic scale being downward. This information is then sent to the brain, which is processed in the medulla oblongata, where it will send impulses to breathe and expel the CO2. And obviously we see the percentages here of where the CO2 actually diffuses out of the muscles. We have the carbonic acid dissolved into the water and the plasma and the fluid, and also the carbohemoglobin. It then goes through the blood and then travels to the lungs, where, again, as I said before, it's expelled by expiration or breathing out, and actually gets rid of the waste product, which helps the body, so that fatigue is kind of decreased as such, or the rate of fatigue. If you're getting rid of this waste product, your muscles won't fatigue as quickly. Second waste product, lactic acid. The lactic acid system is used during the lactic acid system itself is used during medium duration but high intensity, such as a 400 meter sprint. As a result of this, when you're using the lactic acid system, the waste product is lactic acid. That's one of the disadvantages of being in the system itself. The lactic acid system will become the dominant energy system during exercise with medium duration but high intensity, as said before. While the LA system does resynthesize ATP, it does create the harmful waste product, such as lactic acid. This in turn makes the blood more acidic and will cause the blood pH to drop, as said before. It becomes more acidic and the pH level is downwards. The more acidic your blood is, the lower the pH will go. This will cause affinity of hemoglobin and the success of glycolytic enzymes. Hemoglobin picks up all the oxygen, so when we're talking about affinity, it pretty much means the success of picking up all the pairs of oxygens. As a result of all of this, your body won't be able to create large muscular contractions, which will eventually slow you down. This also triggers pain receptors, and that's when the LA has been created. After that happens, the aerobic system will want to take over as you're working aerobically, and intensity has dropped. Although this does a good job for keeping the ATP replenished, it's a very slow process. As you can see here, this is our data that we have. And this was taken during a Wingate test, which is a high intensity test itself. And the first thing and the really key thing with this is we can kind of see a mixed results. I think personally it's not a dead-on positive correlation, but there is some correlation between the amount of lactate there is in the blood and actually the fatigue index percentage. So let's take a look at Charlie White, for example. Charlie White has a lactate of 7, which is actually very high. That's causing fatigue index to be 81%. However, looking at Beth, for example, she has a lactate of 3, and as a result, her fatigue index is lower. However, the odd result is Alex. Alex has a lactate of 5, so it should roughly be between, if the results are correct, between 72 and 81. But it's actually at 61%. This could actually be down to the muscle fibers he has, and he has the right muscle fibers for the exercise, the Wingate. So the final product is heat. 20% of the oxygen we consume goes to the muscles. The rest is actually converted to heat. Most of the heat that we create is actually depleted and isn't used and isn't really kept into the body because the body needs to remain neutral, and this links with the homeostasis. This happens through cooling mechanisms. We cool our body using the cooling mechanisms. We have many cooling mechanisms that allow our body to stay cool and keep at a constant rate. First, we sweat. Sweating allows the body to release the fluid that has a high temperature, and also cools the muscles down because obviously certain levels of hydration as such is reaching the skin and is actually cooling our skin. Another example is our arterioles vasodilate to allow blood to reach the skin in order to cool the blood and skin. This also relieves pressure in the body because the blood's actually moving further away and reaching the surface. Our hairs also flatten on our body. This is to decrease the chance of trapping air, and that obviously creates more heat. All of these work, but sometimes they're not efficient enough to cool our core temperature. During intense exercise, if our core temp goes too high, it can cause hypothermia, which is where your core temperature is too high, and that can actually lead to really horrible consequences. And it has been known that it can kill you if it gets too high, your core temperature. It can actually result in death. So that's all of the products as such. Now we're going to move on to neuromuscular effects. So firstly, this is the role of calcium, and in the sliding firulament theory. So during exercise, and especially long distance or duration exercises such as marathons, muscles can leak calcium while creating movement energy. Initially, this isn't a problem because calcium doesn't actually harm us. The leaked calcium doesn't harm us. However, calcium is used at binding sites where impulses are sent to the muscles. So if we're losing all this calcium, it can cause calcium depletion, which will mean there won't be enough calcium at the binding sites. The calcium plays a crucial role of almost bringing the impulses across to the muscle. So if there isn't enough calcium in the body, the impulses can die or cause the impulse's speed to decrease. This will mean a marathon runner, for example, will have a lack of impulses, which will mean they won't powerfully contract, which will lead to the runner's speed decreasing and affect the result. And it will also cause fatigue, because if you don't have enough calcium, then we're struggling to contract the muscles, and that means you're kind of running on almost nothing, you're running on no impulses. Secondly, for the neuromuscular junction is acetylcholine depletion. During the neuromuscular junction, acetylcholine is present and is a key part for ATP, which in turn is key for the sliding filament theory, or basically movement and contractions. However, if acetylcholine stores are depleted, and not enough acetylcholine reaches the receptor strips, the nerves won't send impulses to the muscle fibers, which means they won't be able to contract, or contract powerfully enough. However, there is a threshold of acetylcholine. If enough acetylcholine reaches the threshold, and the amount of acetylcholine goes over the bar as such, then the impulse will be sent. However, if not enough acetylcholine isn't present and it doesn't go over the line or the threshold or the bar, then no impulse will be sent, and that's actually known as the all or nothing law, pretty much. Secondly, I don't know how to pronounce it. Clarites is the enzyme that breaks down used up acetylcholine. So essentially, after acetylcholine's been used, the enzyme breaks it down and processes it and moves it along, so it preps it to do it again, essentially. However, at times there isn't enough enzymes to actually break down all the acetylcholine and clear it all the way. So as a result, if this happens, then firstly, you're not ready for the next muscular contraction, and that then leads to fatigue due to the performer not getting enough muscular contractions to move forward and almost running on no impulses as such at all. Finally, the final neuromuscular fatigue is action potential. Action potential is a reason as to why fatigue might happen. During exercise, waste products such as CO2 and lactic acid can increase the acidity levels in the bloodstream, which then also means pH, which also means decrease in pH levels. This then slows down the speed of the impulses and such to the muscles and muscle fibers. This is a big problem, because if you lack power or force in contractions, example, if you're doing a marathon, your pH levels throughout the run slowly decrease, meaning the acidity is higher. During the last half mile, your muscle fibers will be heavily fatigued, and the result, slow impulses. The impulses aren't quick, and they're quite weak, which means your contractions are going to be really weak, and that's all down to fatigue and the acidity. So that can affect results, and also going back to before, as soon as the decrease in pH also decreases the peak twitch fibers, which means it isn't actually working your main muscle fibers as well, and you can't actually get maximum power output.